Alas, dear physicist, it is time for our final video in the area of waves and oscillations. You gotta be really happy about that, or kinda sad. I hope you're not really sad. If you love waves and oscillations that much, you can't be human. But let's begin with light waves. Now, light waves are electromagnetic waves, which means there is a disturbance in both the electric and magnetic fields. What does that mean, you ask? Go to the next chapter, I say. We don't have videos on that, you say back. Well, too bad. Read in the book. I don't know. We'll release more videos about that maybe next year. For now, we're just trying to get the first year of physics out of the way, okay? We don't have to discuss this right now. But the electromagnetic wave looks something like this. We've got kind of like a wave that crosses on itself in 2 dimensions. Got this wave here, which is vertical, and this wave here, which is horizontal. I know my artist's interpretation is absolutely horrible, but bear with me. Okay, that is what an electromagnetic wave is. Now, it comes on a spectrum, the electromagnetic spectrum, but all we're interested in here is visible light, light you can see, which is between 400 and 800 nanometers in wavelength. It's a pretty small scale based on like the whole electromagnetic spectrum, but that's good. It's just a small scale that we're interested in here. Now, some facts about light in this sort of area is that different wavelengths for visible light produce different colors. The shorter your wavelength, the brighter your color, the violeter your color. Violet is in the 400 range. 800, however, is a longer wavelength, and that gives you red, which I'm sure you already know. It's the electromagnetic spectrum. It's nothing new. However, another thing that we must know about our good buddy light is that in a vacuum, its speed is constant at 3 times 10 to the 8th meters per second. That's the speed of light in a vacuum. Remember that, because once you know that, you can calculate the frequency from the wavelength and the wavelength from the frequency. And one final thing that I doubt you have heard before is that the intensity of the light, how brightly it shines, is proportional to the amplitude of the light wave squared. What? Yeah, it's not really important till the end of this video, so just keep it in the back of your mind, all right? So now let's talk about light in terms of those 4 things that we talk about for all waves, the first of which being reflection. Oh, yay! So excited. Light will reflect. However, light is special because some objects will absorb the light because it's made of photons, which are like pure little energy particles, but we'll get more to that later. So, some of the light is absorbed when it hits, say, a leaf. Some of that light is absorbed. Some of it is reflected back. So if it's white light and it's hitting it, well, in terms of a leaf, it absorbs red, orange, yellow, blue, indigo, and violet. However, it reflects green. It doesn't like green. And that is why a leaf is green, kids, because it reflects green. It hates green. Yeah, it's kind of horrible that we associate objects with the color that they reflect and therefore hate the most. But let's not get meta here. Let's move on to refraction. Now, refraction with light, well, just like waves, because these are also 2-dimensional waves, just like water waves, we can apply good old Snell's law when moving from, let's say, it's moving from air into glass. Just as an arbitrary example, here's the normal to that barrier of refraction. You got your light, it's coming at you, and then it's refracting down there. Here's the angle of incidence, here's the angle of refraction, and the sine of that over the sine of the other is going to equal the initial velocity over the velocity after refraction. It's pretty simple. However, with light, we have a new concept here, which is called the refractive index. The refractive index for each object is a set value. Now, let's say, I don't know, air has 1 and glass has 30, I don't know. There's a table out there somewhere that you can search up. But with Snell's law, we can also say that the sine of the angle of incidence over the sine of the angle of refraction is equal to the reflective index of, this is, careful here, you gotta pay attention, of the second one. So in this case it'd be 30 if we're applying 30 for glass, over the refractive index for the initial medium. And that's another version of Snell's law that we use for light. That's a pretty straightforward thing there. Now, what about dispersion? What happens when light disperses? Well, higher wavelengths of light will be diffracted more when they're dispersed through a small hole. Let's say you've got a triangle body. Why is it a triangle? I'll explain later. You've got the white light, and it's going to be diffracted through that small hole in the triangle. Well, let's say you've got red, right, and blue. Blue's a higher wavelength. It's going to get diffracted more. It's a higher frequency, the wavelength is smaller. So red's going to keep on going. Blue is going to be all like, "Wah!" And that is the concept behind a prism. That is why when you shoot light into a little triangular thingamajigger, you get a rainbow, because of those dispersion rules of light. Now, there's another thing we have to discuss when it comes to diffraction, refraction. They're kind of the same thing when it comes to light. They're almost equatable. And that is the critical angle. Now, the deal with the critical angle is, at some point, at some surface, on some surfaces, when light tries to pass through, it's just going to be refracted right in the same direction as the line of refraction. That is the critical angle. When the angle of refraction is 90 degrees, that's the critical angle. When you exceed the critical angle, that is called total internal reflection. It doesn't even matter what you're shooting at anymore. That's what happens with mirrors. The critical angle of refraction is exceeded, and all the light is reflected at the exact same angle at which it came in. That's a 30, that's a 30. That is total internal reflection. And that is actually what occurs inside of fiber optic cables. Total internal reflection again and again and again and again and again until the light and the information, therefore, gets where it needs to go. And that is really it. So now we're going to talk about diffraction. Yeah, I bet you forgot about diffraction interference, but we got to talk about those too. What about diffraction of light? Well, there are two ways that light can be diffracted, and interference occurs during the second one. So we're going to talk about interference here too. And what happens there is you get one slit for diffraction. Light passes through one slit, and it's going to spread out. It's going to create a pattern. It kind of looks like this. You've got a bright spot here, kind of less bright splotch, less bright, less bright, less bright, less bright. And that's because when the light diffracts, the highest intensity light is going to be smack dab in the middle, with lower intensity light as you go further out, further out, further out, further out. Now, two slit, when it's diffracted through two slits, that's where the interference gets in, because these light patterns are going to start interfering with each other. And that's going to create a pattern known as the light interference pattern, where you've got a really bright spot here, and then dark, bright, dark, bright, dark, bright. And that is because in these locations, constructive interference is occurring. In these locations, it's destructive. And that is the whole reason behind this crazy cool interference pattern for light. Now we've got two final concepts to discuss with light. The first of which being polarization of light. You remember when I talked about polarization and I said that when you have a wave that's moving in one dimension, it's considered to be polarized? Yeah. Well, light's not one dimensional. It's two-dimensional, as we discussed earlier, because it's electric and magnetic. However, there are some surfaces, when they absorb the light, and it's coming at them with its totally janky electromagnetic deal, it polarizes it, and it comes out moving in but one direction. Totally kicks out all the other multi-directional light stuff. And when light is passed through one of this polarizing filters, is considered to now be polarized light. Polarized light! Now, how can we determine the intensity of this polarized light? Because only some of the light's making it through. The part that didn't make it through either got absorbed or reflected or something. So what's the new intensity? Well, the new intensity of this light is calculated by something known as Malice's law. which is that the intensity of the new polarized light equals the initial intensity of the light multiplied by the square cosine of the angle at which that light, or the unreflected area of the light, is to the new polarized light. What? You ask, what does that mean? Well, let's say you have light going here into this polarizing filter, and this is the dimension you have it in initially. It's like that. However, when it comes out, it's all slanted like this, right? So that's a new one. That's the angle, right there. Because when you go into that light here, the area that makes it through is that. Those are the dimensions that make it through. This is the main preceding dimension before, so it's the angle between the main preceding dimension before and the dimension after. Yep, that's pretty much it. And that is based off of that proportionality equation that we came up earlier for intensity and amplitude, because the new amplitude is equal to this. And there you go. There you go. That is everything that has to do with waves and oscillations. I bid you adieu until we rejoin for electricity and magnetism.